Hello guys, welcome back again. My name is Amit and it's code time. So, another weekend and we are back again with another video. So, this time we'll be discussing the weekly contest 478 which was conducted today. The contest had four problems ranging from easy to very hard problems. Okay. So, yeah, overall, this contest was actually quite good for any beginner who's starting with contest on Leetcode contest. You can go with, you could have tried out this contest. Okay, so we'll also discuss the difficulty level of each problem because to be honest, first three problems were actually very easy, while the last problem was on the very tough side. It was very hard to come up with a logic for the fourth problem, and we'll discuss the solutions. We'll try to discuss solutions for each of them, right? May or may the last solution for the last problem, basically the fourth problem, may not be within the scope of this video, but yeah, we'll discuss rest. We'll discuss the logic at least, and we'll discuss the solutions for the first three problems, right? And yep, let's start with it. Hmm. Okay. So the first question we have is count elements with at least k greater values. So before starting, I saw some reviews regarding this contest today. So some people were saying like second question was easier than the first question, and it actually took some time for the people to differentiate which problem to do first. But to be honest, for any experience, not much experience, but yeah, with an average experience coder, the first three problems would have been a cakewalk. Okay, it was very easy to do the first three problems, not very hard logic, not complex data structures to be used or complex algorithms to be used, right? While the last problem, I think in order to balance out things, the last question was made very hard, very tough, and it actually uses the advanced data structures. We'll discuss them later on. Okay, but let's start for the time being. Let's start with the first question, which we have is count elements with at least k greater values. So let's read the question. You are given an integer array nums of length n and an integer k. An element in nums is said to be qualified if there exist at least k elements in the array that are strictly greater than it. Return integer denoting the total number of qualified elements in nums. So what the question says is, let's say you are given an array. You basically have to tell the number of qualified elements. And what is a qualified element? Any element which has at least k elements bigger than it in the nums array will be a qualified element. For example, let's take the first example. We have 3, 1, 2. When k is 1, so any element which has at least one or more bigger element than it would be considered as a qualified element. For example, 1 has two elements bigger than it, 2 and 3, so it's a qualified element. For 2, we have 3, so again 2 is a qualified element. While 3 does not has any element which is bigger than it, so it will not be a qualified element. So total comes as 2. In similar way, in example 2, we have three fives and k is 2. So as we can see, all the elements are 5. That's why no qualified element can be found because there is no bigger element than 5, right? The constraints are the length of the array goes to the power of 5 and the values go up to the power of 9 and the value of k starts from 0 and goes up to n minus 1, basically less than n. Okay. So I think this is a pretty straightforward problem, not a not complex logic involved. But yeah, let's discuss the solution for this. Okay. So first of all, to the main thing that anyone I think would have been able to figure it out, that we should first sort the array. Okay, we should first sort the array. Why? Because we need what we need the count of bigger elements, right? We are not interested in how elements are aligned, okay, which number comes after another, but we basically have to count. We have to get a count. So no issues in sorting the array. So first you sort the array, and the first naive thought which will come into your mind is basically removing the last k elements. Okay, let's say we have an array of size n. Okay, let's mark it as question 1. Let's say we have a array of size n, and after sorting I remove the last k elements, which will basically denote the k biggest elements, right? If I remove the last k elements from an array, right, it basically is equivalent to removing the k biggest elements, okay, because it is a sorted array. Okay, if I remove these k elements from the last of the array after a sorted array, we will get n minus k elements, which will be what? Which will be our qualified elements, right? Because for all of these n minus k elements, we have at least k bigger elements, right? And that is why the answer could have been n minus k in case our array would have all unique elements. Okay, let's say if our array would have been having all the unique elements, then you could have just directly return n minus k. Okay, direct n minus k would be our answer, no other thing, right? In that case, you wouldn't even need to sort the array because you know that all the elements are unique. That's why removing the last k elements would give you n minus k elements, which are the total of qualified elements. But in our case, it might be possible because we have a repetition of elements. So let's take a case like 2, 3, 3, 4, and 5. Okay. So let's take k as 3. Let's take k as 3. So, this array is sorted. We have taken a sorted array. So removing the last three elements, we remove 5, we remove 4, we remove 3. So this would mean that both these 2 and 3 would be a possible answer because we have removed, k elements. So what? 5 minus 3 gives 2. So 2 should be our answer. But no. Why? Because this 3 also does not have 3 bigger elements than it, right? It is same as the as this element, right? So therefore, this 3 also does not have a property of qualifying into qualified elements, right? So that's why we should not count this element too. So for removing this, what we can do is basically sort the array, start a pointer from the end of the array, okay, and move it till either we remove k elements, okay, and we remove the repetitions as well. And we remove the repetitions as well. For example, in this case, we could have stopped at this 3, but since we know that this 3 continues on the left side, we would have to move the pointer far, right, far on the left, because these elements can also not be counted as qualified. Okay. So after the end of this, loop, we'll finally see our pointer points at the first element, and therefore we only have one element which is qualified. Okay. So let's go to the implementation part. Okay. So here we can see what we have done is first taken the size of the array, then sorted the array, then we take a back pointer which starts from the back of the array, and then we move either our pointer moves to 0, right? Let's say if k is very big, then we might not be able to find any qualified elements. Array will go less than 0, right? And while k is also greater than 0, because we have to remove the last k elements, right? So what do? We start removing the elements, and we keep on removing the elements until we have removed all the repetitions, right? Until we have removed all the repetitions, right? Like c is nums of I, and if the alternative element, which is basically the next element on the left, is equal, it will keep on moving until we have removed at least k or more elements. Okay. Why k or more? Because in case of repetition we might remove more than k elements, right? And finally, wherever our pointer stops, whenever the k becomes less than or equal to 0, this means that we have removed at least k elements. हमने कम से कम k elements तो remove कर ही दिए हैं. It might be more than k क्योंकि repetitions की वजह से, right? And finally we return l plus 1, which is our pointer plus 1 value, because we need the count in one base indexing. And the time complexity for this approach would be n log n, because you have sorted the array, and order n basically needs a pointer, so overall time complexity is n log n. And space complexity is order 1, because we haven't used any array or array or a vector of any particular size n. We just have we just have used variables. So that's for the first question. Let's jump to the second question, which was, to be honest, was one of the most easiest question, okay, of this complete contest, which is, you are given a string s consisting of lowercase English letters. So first of all, we know that our strings contain only lowercase English letters, which is basically lowercase alphabets from A to Z. Return an integer denoting the maximum number of substrings you can split s into, such that each substring starts with a different character. Okay, no two substrings start with the same character. Okay, let's see an example. First example is like AB, AB. So we know the max we can get is basically one starting from A and one starting from B. So one possible answer could be taking A and BAB. Another possible answer could be taking ABA and B. In a similar way, we have ABCD. So we can see we can have 4 at max substrings starting from different characters. Okay, and in the last test case, we have all A's. So yeah, we have only one unique character. So only one possible substring which starts with a different character, right? And the length of the string goes up to the power of 5 and only lower letters. So this problem is actually very easy. The first observation that you will have is basically that let's try to understand कि, we need to get the maximum number of substrings that start with a different character. First of all, understand how many different characters can we have for each substring. So since it is said that we can only have lowercase English letters, which is basically 26 alphabets. So this means in any case, our answer can only go up to maximum 26, right? We can have at max 26 different starting characters for each substring, right? We cannot go more than that. And that is where our problem ends actually. So what you do is basically run over the complete string. Okay, that's just start uh, you know loop over the string, and wherever you see a different character, let's say for example we had a b, so what you can do is whenever you encounter a new character, right, which was not present in the string earlier, you can mark it as a new substring, right? Because now we have got a substring which starts with a different character, right? So what you do is, the logic is very simple. Wherever you find alphabet which has not been seen before, you can mark it as true, right? And basically all these characters would contribute to getting you the maximum number of substrings you can get. So what you do is create a 26 size subarray, loop over the string. Wherever you find a character which has not been marked among the 26 alphabets, you increase your answer count, because that is going to contribute to your distinct character substring, right? And then you mark it as true, just because you don't want to mark it again, because it has already been counted, right? And then return the answer. So the time complexity is order 1, the time complexity is order n, okay, because we are only going to loop over the string. And the space complexity is order 1 because we are using a fixed size array. Okay, let's say even your array is in power of 5, or let's say tomorrow it becomes in power of 6, but still we only are using 26 sized array. That's why it's order 1. So that was the second question, which was actually the easiest question of the whole contest. Okay, now let's go to the third problem. Now third problem is also very interesting. Okay, it's very interesting but not very difficult. Okay, it's interesting but not difficult at all. So let's discuss this problem. So the name of the problem is minimum absolute distance between mirror pairs. Okay, so you are given an integer array nums. A mirror pair is a pair of indexes I, comma j, such that 0 is less than equal to I less than j less than n. Okay, I is less than j basically. Return nums of I, reverse of nums of I is equal to nums of j. So basically when you reverse the number nums of I, you get nums of j. So remember that j has to be after I. Okay, so ith element, basically I is denoting a position which is smaller than j. Okay, so jth element is to the right of ith element, and the reverse of the, nums of I, basically the element at the ith position, the reverse of it should be equal to nums of j. Okay, and reverse basically denotes the integer found by reversing the digits of x. Okay, leading zeros are omitted after reversing. So for example, when we reverse 120, it becomes 21 and not 210. It does not becomes it does not becomes 0 to 1. Sorry, it does not become 0 to 1. Okay, we have to omit the the leading zeros, because we know that leading zeros have no values. And then return the minimum absolute distance between indexes of any mirror pair. The absolute distance basically absolute of I minus j. So हमें क्या करना है? We have to find the minimum distance for any reverse pairs or mirror pairs that exist. Let's say हमारे पास कोई I, j है, such that they are mirror pair, right? Such that reverse of nums of I is equal to nums of j. Then you take its absolute difference. Among all the possible pairs that can be formed out in this array, you have to find the minimum difference that is possible for AB absolute value of I minus j. Okay, basically j minus I you can say, because j always has to be bigger than I, right? Okay, and if no mirror pair exists, then you have to return -1, which is the default value. Let's go to the first test case. We have what? 12, 21, 45, 33, and 54. Let's start with 12. Okay. So for 12, what is the reverse of 12? It's basically 21, right? It is basically 21. So we can see 21 exists in the array. और उसका position क्या है? उसका index है 1 और 12 का index है 0. So 1 minus 0 is basically 1. So एक possible pair है. 21 के लिए हम देख सकते हैं on the right hand side उसके कोई भी नहीं है. For 21 we can see on the right hand side we have no element present जो कि उसका reverse करता है. याद रखना, do not have to look on the left side but on the right side. Remember, I has to be less than j. So whatever element we are considering at this position at this time, उसके right पे ही देखेंगे, उसके left पे नहीं देखेंगे, right? So reverse of 21 क्या exist करता है? Left पे करता है पर right पे नहीं करता है. That's why no use for 21. Then we go to 45. 45 का reverse क्या है? 54 है. So we can see कि 54 exist. 45 का index है 2 and 54 का index है 4. So 4 minus 2 is 2. So already हमें 1 मिल गया था, तो minimum of 2, 1 is 1. ठीक है. Then we go to 33. 33 जो है 33 का रिवर्स 33 होता है, बट नाउ द प्रॉब्लम इज कि हम सेम इंडेक्स पे नहीं दे सकते ना. आई हैज टू बी लेस देन जे. इट कैन नॉट बी इक्वल टू जे. अगर इक्वल टू जे होता तो 0 एक पॉसिबल आंसर होता, but here we know that I has to be less than j. Therefore, reverse of 33, although it is present in the array, but because of non-equality condition कि I और j different indexes होनी चाहिए, 33 would not contribute to the answer. Then we again get 54. 54 आखिरी एलिमेंट है, उसके राइट पे वैसे भी कोई एलिमेंट एग्जिस्ट नहीं करता है, so we can omit that. So after getting all the mirror pairs, we can see the minimum difference possible was 1, which we got from 12 and 21, right? In a similar way, we can see 120 and 21. So now we start with the first element 120. 120 का reverse करने के बाद 21 आता है, 0 1 2 नहीं आता है. Remember, because we do not include the leading zeros, they have no values, right? So reverse of 120 exists on index 1. So 1 minus 0, again you get the value difference as 1. Then you move to 21. 21 के right hand side पे there is no element. So again, कोई बात नहीं, we cannot consider it. And we got the answer as 1. Now let's take the same example here. We have what? 21, 120, but now their order has been reversed. Remember, the example 2 and example 3 are very similar. Only the order of the elements has been reversed, which will actually change our answer. Now, when you reverse 21, what do you get? When you reverse 21, you get 12. You get 12, 1 to 12. You do not get 120. You get 12. So we can see the mirror pair for 21, which is 12, does not exist in the array. So therefore, we can actually leave this. Then we have 120. 120 ka reverse 21 is, okay, 21, reverse of 120 is 21. But the problem is the mirror pairs index should be greater than ith index, right? अगर इसके राइट पे अगर होता, अगर 21 इसके राइट पे होता, तो इट वुड हैव बीन अ पॉसिबल आंसर, बट वी कैन सी 120 के राइट, 120 तो खुद ही क्लास एलिमेंट है, दैट्स व्हाई वी हैव नो एलिमेंट ऑन द राइट, तो ये भी कंट्रीब्यूट नहीं कर पाएगा. दिस मींस वी हैव नो मिरर पेयर्स इन द एरे. Okay, and that is why the default value, which is -1, we return that. Constraints are n is 10 to the power of 5, and value in the area 10 up to 10 to the power of 9, right? अब इसको समझने की कोशिश करते हैं. ओके, फर्स्ट ऑफ ऑल व्हाट ऑर्डर शुड वी फॉलो, हमें क्या ऑर्डर को फॉलो करना चाहिए, पहले समझते हैं. रिमेंबर, let's say the naive approach, which is the naive approach, what we can think of is, let me just change my view. Okay, the naive approach for this problem would have been, आप क्या करते हो, क्वेश्चन 3, what do, you pick up a nums of I, आप nums of I उठाते हो एक, right? You get its reverse, let's say, let's call it x, let's call nums of I as x, we get its reverse, and then try to find this element reverse of x in the range from I plus 1, let's say it is the I equation, up to n. Okay, this is what we do. Okay, so what do we do, starting from reverse of x, starting from the I plus 1 position, because we know that j has to be bigger than I. So what do, we first of all pick up an index, which is I, take the nums of I, regard it as x, we find the reverse of x, and then we try to find this reverse of x in the range from I plus 1 up to n, and whatever is the first occurrence where we find reverse of x, we take the difference to get the the minimum absolute difference, right? क्योंकि जो भी नियरेस्ट होगा I के नियरेस्ट क्या होगा, लेट्स से I प्लस y लेते हैं और i प्लस जेड लेते हैं, वेयर y इज लेस देन z, तो i प्लस वाई ज्यादा पास होगा या i प्लस जेड ज्यादा पास होगा, सिंपल सी बात है, i प्लस वाई ज्यादा पास होगा. सो व्हाट यू डू इज बेसिकली स्टार्ट अ लूप फ्रॉम i प्लस 1 गोइंग अप टू n, एंड वट वेर एवर यू फाइंड द फर्स्ट अकरेंस ऑफ रिवर्स ऑफ x, दैट विल बी योर पॉसिबल पोजिशन, यू टेक द डिफरेंस एंड यू ब्रेक द लूप. Okay, in the worst case, we'll go until the end of the loop, let's say reverse exist nahi karta, in that case every time we would have to go to the end of the array. That's why the time complexity of this naive approach would be order n to pick up the elements, and an additional order n to find the possible existence of a mirror pair. So we get an n square. Okay, but this is not an optimal approach, right? This is not an optimal approach because this will give it really. So what do we do now? So देखो, रिवर्स फाइंड करने का जो कोड है वो तो फिक्स है. ओके, रिवर्स, तो आई थिंक दिस शुड बी अ वेरी डायरेक्ट अप्रोच. आई थिंक फाइंडिंग अ रिवर्स ऑफ अ नंबर इज अ वेरी बेसिक थिंग दैट यू लर्न इन नंबर थ्योरी, कि एक नंबर को रिवर्स कैसे करना है. यू जस्ट एक्सट्रैक्ट द डिजिट्स एंड यू कीप ऑन मल्टीप्लाइंग एंड एडिंग द रिमाइंडर इन द रिवर्स ऑर्डर, एंड यू गेट द रिवर्स ऑफ द एलिमेंट, राइट? सो आई थिंक रिवर्स ऑफ द फाइंडिंग द रिवर्स इज फिक्स्ड. ये तो आपका मान लो log x टाइम लेता है. ओके, दिस इज फिक्स, इसको आप ऑप्टिमाइज नहीं कर सकते. ओके, दिस इज फिक्स, फाइंडिंग द रिवर्स हैज टू बी फिक्स, क्योंकि वो हमें चाहिए ही चाहिए. व्हाट कैन वी डू डिफरेंटली, ये जो बार बार कंपटीशन हमें करना पड़ रहा है, राइट? एवरी टाइम वी हैव टू कीप ऑन कंप्यूटिंग कि भाई ये प्रेजेंट है कि नहीं है. व्हाट वी डू इज, since we know since we know for any i element, we always have to look in the direction from what, I plus 1 in up till n, correct? हमेशा किसी i के लिए we have to look forward in the range from I plus 1 up to n. क्यों ना हम इस एरे का जो कंपटीशन है वो बैक से स्टार्ट करें, इंस्टेड ऑफ स्टार्टिंग फ्रॉम द फ्रंट, व्हाई डोंट वी स्टार्ट फ्रॉम बैक? ठीक है, रिवर्स पेयर तो फिर भी हमें मिल ही जाएगा ना. ठीक है, सो व्हाट डू वी डू, we start we start the calculation of mirror pairs and existence of mirror pairs. Instead of starting, we start from end. ठीक है, क्योंकि हमें पता है we always look towards the right of an element to find a mirror pair, right? So हम सीधे बैक से स्टार्ट करते हैं. Let's take an example, जो कि हमारा पहला एग्जाम्पल भी था, आई थिंक 120, 21, then 45, then 33, then 54. Okay, now what do we do? Let's start from the back of the array. Okay, we come to 54. We find the reverse of 54. Okay, the reverse of 54 is what? It is 45. अब हम क्या करते हैं, we also maintain a map, okay, to index basically the values. ठीक है, just to find the index of the value, कि कोई वैल्यू किस इंडेक्स पे आई है. So basically यहाँ पर आप nums of i को डालोगे, and here you will update the index, okay, after the calculation, but not before the calculation. Okay, so this is for maintaining the recent index, the most recent index where a particular element was found. Let's say 54 के 2 रिपीटेशन होते हैं, तो 54 का बाद में एलिमेंट जो इंडेक्स है वो फिर से अपडेट हो जाता. सो दिस मैप इज बेसिकली फॉर मेंटेनिंग द मोस्ट रिसेंट अकरेंस of the element nums of 5. और याद रखना, we are iterating in the backward direction. I told you because we always need to look in the right direction. So now we start from 54, we get 45. We check, is 45 present in our map? Initially our map was empty, right? Initially our map would be empty, इसमें कुछ नहीं होगा. So we try to see if 45 is present in this map. We can see 45 is not found. This means 54 does not has a mirror pair, right? क्योंकि उसके राइट पे कोई नहीं है, that's why you can also see it's not giving you an answer. Okay, so this means कि भाई इसके लिए आंसर एग्जिस्ट नहीं करता, we have to go to the next element, right? And before going to the next element, what do we do is we insert the current element into the map. So MP of 54 becomes what? Let's index these numbers 0 1 2 3 4, right? So MP of 54 becomes 4, right? ये हमें मिल गया. Now what do we do? Now we move to 33. We find the reverse of 33, which is again 33, right? We check in the map. Do we have 33? अभी तक 33 आया ही नहीं है. लेट से कल को दो 33 होते तो पॉसिबल होता, क्योंकि हम एक 33 को पहले प्रोसेस करते, उसके बाद वी वुड हैव मूव लेफ्ट एंड वी वुड हैव फाइंड अनदर 33. उस केस में ये वाला 33 और ये वाला 33 मिरर पेयर बना रहे हैं. बट सिंस वी हैव ओनली अ सिंगल 33, इट कैन नॉट फॉर्म अ मिरर पेयर अलोन विद इटसेल्फ. ठीक है. सो व्हाट डू वी डू? वी ट्राई टू फाइंड 33 इन आवर मैप, बट वी कैन सी इट्स नॉट देयर, राइट? सो इसको भी हम omit कर देंगे बिकॉज नो पेयर, एंड वी विल आल्सो पुश दिस 33 इनटू आवर मैप. सो वी हैड 54 जिसका इंडेक्स अभी 4 था, और 33 का इंडेक्स भी हम अब पुश कर देंगे इसमें. 33 इज व्हाट? 33 इज 3. तो अभी हमारा मैप ऐसा दिखता है, राइट? नाउ वी मूव टू 45. व्हेन वी गो टू 45, व्हाट डू वी सी? द रिवर्स ऑफ 45 इज 54. Okay. Now, when we look up in the map, do we have 54 in our map? Yes, we have a 54 in our map. हमारे पास ऐसा एलिमेंट है. So what do? We take the index of 54, which is 4, क्योंकि हमें पता है ये सब राइट में आ रहे हैं. So this means कि ये इंडेक्स ऑलरेडी बिगर होंगे करंट इंडेक्स से, राइट? सिंपल सी बात है, सिंस वी आर मूविंग इन द बैकवर्ड डायरेक्शन, ये जो एलिमेंट्स हमने ऑलरेडी डाल रखे हैं, दीज द पोजिशन और द इंडेक्स ऑफ दीज एलिमेंट्स वुड ऑटोमेटिकली बी बिगर देन द करंट आई, क्योंकि हम बैकवर्डली मूव कर रहे हैं, राइट? सो व्हाट डू? हम 54 का इंडेक्स क्या है? 4, वो मैप्स उठाते हैं, एंड द करंट इंडेक्स इज व्हाट? करंट इंडेक्स इज 2. 45 का इंडेक्स क्या है? 45 का इंडेक्स है 2, राइट? इज इट विजिबल? या 45 का इंडेक्स है 2, राइट? वी टेक द डिफरेंस. तो हमारा जो आंसर करंट था, हमारा जो करंट आंसर था, वो अब 2 बन चुका है. इनिशियली इट वाज -1, या फिर आप कुछ और डिफॉल्ट वैल्यू ले सकते हो. ओके, आई थिंक इट्स गोइंग इन आउटसाइड. ओके, so this will become 2. Okay, and then we'll also push this 45 into our map. So अब क्या हो जाएगा? मैप में 54 4 आ जाएगा, 33 का 3 आ जाएगा, एंड 45 का 2 भी आ जाएगा, राइट? Then we move on to the next element. The next element is what? The next element is basically 21. I think, yeah, it's 21. So 21 का रिवर्स होता है 12. We look up in the map, we find that it's not present there, we do not calculate it, answer still remains 2, and we push it into the map. 54 is 4, 33 is 3, 45 is 2, and 21 is 1, right? And then we finally move to the first element of the array. Okay, first element जो हमारा था, which was 120. So reverse of 120 is what? It's 21. Remember, we have to exclude that leading zeros, right? उनकी कोई values नहीं है. Now we look. Do we have a 21 in our map? Yes, we have, right? तो डिफरेंस क्या हो जाएगा? 21 का इंडेक्स था 1, एंड करंट इंडेक्स क्या है? 0 है. सो व्हाट डिफरेंस डू वी गेट? वी गेट एज 1, एंड आंसर अभी हमारा 2 था. आंसर बिकम्स मिनिमम ऑफ 2, 1, क्योंकि हमारा इनिशियल वैल्यू 2 था. इट बिकम्स 1, और हम इसको भी पुश कर देंगे. फाइनली आवर मैप लुक्स लाइक दिस. 3, 45 is 2, and 21 is 1, and 12 is 0. 120 is 0. So finally we come to the end of our loop, and we have found our answer as 1. You just return this. So in this way, we'll be efficiently be able to calculate the mirror pairs and the minimum difference between them. Let's look at the code part. Yeah. So see, what do we have? So first of all, we create a map, which is basically for storing the most recent occurrence. Then we have answer variable, by default int max, because we have to take the minimum. Then the maximum element, well, this is not required. You can actually remove this, not required. Okay, and then you basically start iterating in the backward direction. First you get the reverse of this number. Reverse code is this basically. After getting the reverse, you check if that element exists in the map or not. If it exists, then you can directly take the difference with I, that, and you minimize this difference. At the same time, you update the location or the index of that particular number, and in the end you just return. If it's int max, this means we were not able to find any mirror pair, and we return -1, else we return the answer. The overall time complexity of this approach is basically order n into log x, you can say, or log max of x. So basically this computation of reverse will take log x time. Okay, let's take an upper bound on x, which is basically the maximum number in the array. So we can say it as n into log of max of nums, basically the maximum number in the nums array, right? So that is the time complexity. Space complexity we have, since we are using a map which can at max take up n elements if they are all unique or whatever is, yeah, let's say they are all unique. So in that case we have what order n space. So that is how we solve the third problem. So to be honest, the first three problems were very easy. Any experience or any coder who has spent a lot of time in giving the contest and problem solving might be able to do in the best case in within 15 minutes. Within the first 15 minutes, these three questions can be solved very easily. Okay, the first two problems take minimum of what 2-3 minutes each, and this writing the code for this problem and coming with the solution for this problem will take what 5 to 6 minutes or 7 minutes. So overall, I think it should be within 15 minutes for an experienced coder, right? For an experienced coder who has been giving contests for a lot of time. For an average coder, you can take up to 30 minutes. Okay, and a since a normal contest is around for 2 hours or 1.5 hours, so the first 30 minutes, would be spent in solving the first three problems. Given these three problems because they were very easy, then we finally move to the fourth problem. Finally, move to the fourth problem. I'll not show the solution for this problem because I think the solution for this problem, the proper code for this problem, would be a very complex thing. It might uh, go over the head. Okay, so first let's discuss the problem. What is the problem? I think in order to balance out the easiness of the first three problems, they gave a very tough problem, a very hard problem in the end. Okay, it is very difficult to come up with a logic for this, and even if you come up with a logic, the implementation part is very long, is very lengthy and hard actually. Okay, so let's understand the question first. We have minimum operations to equalize subarrays. You are given an integer array nums and an integer k. In one operation, you can increase or decrease any element of nums by exactly k. Okay, by exactly k, remember this. You are also given a 2D integer array queries where queries of type li, ri, that is basically a range is given. For each query, find the minimum number of operations required to make all the elements in the subarray nums li, ri equal. If it is impossible, the answer for that query is -1. Return an array answer where answer of I is the answer for the ith query. So what you do is basically you are given an integer array num and you have been given an integer k. So what you can do is in any one operations you can either increase an element by k or decrease the value of that element by k. Increase or decrease by k. Then we have been given queries of type range, basically starting point, ending point, LNR. For any subarray, we need to find out what are the minimum operations to make all the elements in that subarray equal. Okay, we don't have to directly modify the array. Okay, but we have to tell the minimum number of operations for converting so. If it is impossible, for that query, we can return -1. And in this, we have to return the complete array. Okay, let's take the first example and then we'll go on to discussing a bit of logic. So first we have 147, k is 3, queries are 0, 1, 0, 2. Let's say if we take the first query, which is 0, 1. So let's try to see if we can convert 1, 4, basically 1, 4, this subarray to an equal element. Let's say I want to convert this whole, subarray into 4. So what do I do? What do I have to do is 4 is already 4. For increasing 1 to 4, we just have to apply one operation. 1 plus 3 will give you 4. So therefore, to convert this subarray into equal elements, we just have to apply one operation. So here we have 1. Then we have 147. In case of 147, which is basically 0, 2 query. So we have all the three elements. You can see here basically again let's choose 4 as our middle value. So what do? We convert 1 to 4 in one operation by adding 3, and we also convert 7 to 4 by subtracting 3. So therefore, in two operations, we can make a subarray which is consisting of complete equal elements. So 1, 2. In a similar way, let's take 1 to 4. We have k as 2. When we take 0, 2, we get -1. So we don't have a possible answer for this subarray, right? Then directly let's come to the constraints. Constraint is what? Nums of length is basically 4 in the power of 4. Okay, you remember this 10 to the power of 4. Then nums of I is in the power of 9. Then k is also very big, not an issue. Then query number of queries are also similar to the size of n. Then queries are li, ri, and yeah, ri would always be bigger than equal to li. Okay, I think this much is clear. So first of all, the first thing that we should look on is what are the cases when the answer would not be possible. Okay, see, when we have an answer, when we have a possible answer and then calculating it is actually easy because now we at least know that answer exists, right? Then there should be a strategy to calculate it, but before that it's important to check if the answer even exists or not. Okay, so first of all understand when they are giving us a sub array l comma r, right? L comma r, and we need to convert them to all equal elements, and the operation is of type what? Plus k minus k, right? So let's say we have a nums of I, what operations can we do? We can do plus minus k, correct? We can do plus minus k. Now understand, if we are increasing or decreasing any element by k, by plus minus k, okay, so the resulting element would give the same remainder as the initial element. Now I'll tell you what I mean. For example, in the first case, we had 1, 4, and 7, right? And k was 3. Now I'll tell you why it was possible to take this complete subarray. Now, if you take remainder of 1 with 3, we get 1 mod 3 is what? 1. 4 mod 3 is also 1. 7 mod 3 is also 1. It was this reason why we were able to convert all these elements into equal elements. Let's say this parity was different, then it is not possible to convert to an equal element. Let's say our target element was something like this. Something like this. Okay, T was like a target element where we wanted to convert. Okay, so basically your T should also have the same remainder. Okay, if we take mod on both sides, if we take mod on both sides with k, what do we get? We get nums of I mod k. Okay, so y mod k, because this plus minus k के साथ में mod तो zero आ जाएगा, right? K mod k is zero, should be equal to t mod k, should be equal to t mod k. So basically whatever the target element is, ठीक है, उसका और बाकी जो आप जो भी एलिमेंट लेने वाले हो उनका जो रिमाइंडर आना चाहिए दैट शुड बी सेम. एंड सी बेसिकली ये टारगेट एलिमेंट जो है इसी के इक्वल हमको सबको बनाना है. दिस मीन्स वट एवर सवेरे एल अप टू आर वी आर गिवन, all should have the same remainder when taken modulus with k. So should be equal to this should be equal to keep on going up to a of r mod k. The remainder when divided by k should be equal for all of them. Okay, it should be equal for all of them. If it's not, then it's not possible to find our answer. Okay, remember this. If these remainders, if for the given subarray, the remainders that we have, if they are not equal for the complete subarray, then it's impossible to find an answer. It is हम show कर चुके हैं with this formula. We are basically trying to increase or decrease. So आप plus minus k के जगह पर, let's say if you perform some n operations or m operations, so वो तो कट ही जाएगा because it's a multiple of k. So when you take mod on both the sides, what you get? You get nums of I mod k should be equal to target value mod k. This means जो भी target value है, we want to convert all the elements into the target value. This means the parity, basically the remainder which we get on dividing by k, should be equal for the complete subarray. If we get at least any one element which does not satisfy this condition, which has a different remainder than the others, we wouldn't be able to convert the complete subarray into equal elements. That is the first thing, first observation, right? So what you can do is basically for applying a check, you can first uh, take remainders for all the array, for the complete array for each and every element. Then wherever you see the next element or the remainder from the next element is different from the current one, you can basically increase a counter value, or you can, there are a lot of ways, but what I have thought is basically you can use a counter, right? And then let's say you are given an lnr, what you do is basically you check if the count of r minus count of L minus 1 is greater than 1. This means that we have at least two different remainders in the subarray, and therefore we won't be able to find an answer. If this is equal to 1, this means we would be able to find an answer. Okay, now comes the tricky part, which is basically calculating the solution. Okay, so first of all, remember what candidate should we choose for conversion. Let's say we have an array L to R. Okay, what should be the first thing that what should be the first observation or first approach to basically get the candidate for conversion? So what should be the target element t, right? So target element t तो basically इतना पता है उसका remainder same होने वाला है, but what should it be? ये तो simple सी बात है, इन सबका remainder same होने वाला है. We've already satisfied that condition, right? So the first someone might think would be taking the average of this complete subarray, right? अगर इस subarray का average ले लो, so average is not very difficult thing. You can actually compute prefix sums, and you can just then divide by what r minus l plus 1 length of subarray, and you can get the average. That should be your middle value. And then what you will try to do, you will try to convert all the elements in your subarray to this average value, right? But is it correct? Is this approach correct? Let's say कल को मैं, to be honest, when you are taking small examples जहाँ पर values बहुत differ नहीं करती हैं, you will see कि more or less your this average approach is working. But there are edge cases where you will see that this is not the correct answer. Let's say we have 1 comma 1 comma 1 comma 1, we have 4 ones, and then we have some value like 106. Okay, 106. So the remainders for all of them is basically 1. K is 3. Let's take K is 3. K is 3. So what you see is basically that if you take average of this complete, so it is possible to convert it into equal elements, but if you try to average it, what you will get? You will get 110 divided by 5, you get 22. So what this approach says is convert all the elements to 22. That should be the correct way to do, right? But let's see how many steps it would require. Let's say if I try to convert all the elements to 22, then we have four ones, and each one will take how many operations? Since we have 22 is the final value and 1 is the initial value, and every operation increases or decreases by 3. So what do we get? We get 4 into 7, 28. So this means converting all these four ones to 22 would take 28 operations. Then we also have 106. 106 minus 22 will give you 84, since we have only 106. So right, then 84 divided by 3 will give you what? Will give you what? 3 to the 6 and 3 8 the 24. Okay, is it correct? 28 3 is 324 2 3 to 6. Yeah, okay, 28 only. 28 only, right? So we have 28 operations, one, from 106. So total operations we have what? We have 56 operations which we need to do, right? So this means if we want to convert this complete subarray into 22, we would need 56 operations, which was the average way, right? But let's try to go for a different approach. Let's try to convert all these elements to one. All these elements to one. So what do we see? All these initial ones are already equal to 1. So we don't need any operations. We have only 106, right? Let's subtract 106 minus 1 because there is only 106. And each operation will update by 3. So divide by 3. 105 divided by 3 gives you 35, which is much less than 56. So here you can see, that the optimal approach is not always choosing the average. Then what should be the thing to choose here? The best way to get the candidate, basically the target candidate, would be actually the median of the array, the median of the subarray. Okay, so whatever subarray we are given, L comma R, okay, if we find the median of the subarray, that would be the best candidate. Okay, you can actually try it out, and it's also in number theory. You can also go and read in the stats that median would be a very good candidate for converting all these elements into a equal possible value with minimum operations. Okay, this is a very famous problem actually. Okay, we are actually boiling down to a very similar problem, which is basically finding the minimum absolute difference. Okay, where you basically try to come up with a best candidate, and that is generally the median of the array. But here there is a problem. Here we see, here we are basically working with sub arrays, not the complete array, right? So let's say we have, like this sub array, this sub array which is from, L1 to R1, right? L1 to R1. Let's say in the next query we have some sub array like this, L2 comma R1, L2 comma R1, right? The problem is the median does not persist. The median of subarray L1 comma R1 is not essentially equal. It may be, but it's not essentially equal to median of this smaller subarray L2 comma R1. Here where things go complicated, you can median directly find नहीं कर सकते, right? So here what we do, okay, so what I'll do is I'll just skip over how will you find it, but for as of now, let's say कि हमें median मिल गया. Let's say हमें median मिल गया. Let's say we were able to find the median value. Okay, हमें median L comma R मिल गया. Let's say this element is what, M. Okay, then what we have to do? Then what we have to do is just find in this subarray L comma R, find the elements which are less than k and which are greater than equal to k. So हमें पता है इस subarray का length क्या है, R minus L plus 1 है. Okay, so let's say the number of elements less than m, less than है ये, less than m is equal to x, right? Then elements greater than equal to m would be what? Would be equal to r minus l plus 1 minus x, करेक्ट? क्योंकि यही हमारा लेंथ ऑफ सबैरे है. सो अगर हमारे पास इस सबैरे में x एलिमेंट्स ऐसे हैं जो कि हमारे मीडियन m से छोटे हैं, then we already have what, r minus l plus 1 minus x elements which are bigger than or equal to m. Okay, so now what do we do is कि sum of lesser elements जो कि हमने निकाले थे, ओके, इनका सम, ठीक है, and let me rewrite proper. Okay, for any query the answer is basically what? The answer is basically what? uh, the sum, not sum, we can say it as m into x, which is basically the median and the smaller number of elements, minus the sum of smaller elements. ठीक है, smaller elements, let's call it as sm. Okay, plus uh, plus what? Sum of bigger elements, sum of bigger elements, let's call it as sb, minus r minus l plus 1 minus x into m. So this is basically the formula for calculation of the total number of operations that you need. And at the end, you just have to divide this complete sum that you get by 3 by k. That will give you the final number of operations. So what do we get? What do we get is, let's say at the end somehow we were able to find the median, right? We were able to find the median, the sum of smaller elements, everything. Then we just have to, yeah, then we just have to find what? We have to find m into x minus sm plus SB, which is bigger, elements which are basically greater than or equal to m, minus r minus l plus 1 minus x into m, right? And then this whole divided by k. This will basically give you your answer. So for any query that we get, we first find the median. Okay, we also keep a track of the sum of the elements, right? Let's say we have some efficient data structure, we have some efficient algorithm, which will basically help us in finding the sum of the smaller elements, some of the bigger elements, and the median element, right? Then we can just put in this formula where m is the median that we wanted to get. Basically, क्योंकि हम सब array में काम कर रहे हैं, the median can change, that we have already seen, right? So you get the median for that sub array. Then you count the number of elements which are less than m, which is basically x, and indirectly, directly you have seen that length of the subarray is r minus l plus 1. So bigger elements or greater than equal to m would be basically r minus l plus 1 minus x, and that is also multiplied by m to get the bigger count. So how many operations do you need to convert the smaller elements into m, and how many operations do you need to convert the bigger elements to m, right? Smaller elements के बीच में आप अपडेट करोगे ऐसे, और bigger elements के केस में उनको डिक्रीज करोगे, इंक्रीज और डिक्रीज है. Now why don't we do it directly एक साथ? Okay, why don't we, we could have done this, that हम पूरे सवारी का सम ले लेते हैं और डायरेक्टली माइनस कर लेते हैं कि what do we require. Let's say we could have taken also this. Okay, we would have also taken the sum of complete सवारी minus r minus l plus 1 into m. Do you think this will be correct? This might not be correct. Why? ऐसा समझो, let's say we have some smaller elements जिनको increase होना है, right? And then we have some bigger elements जिनको decrease होना है. When we add them up, the problem is जो smaller elements का जो difference है उसको bigger elements compensate कर लेंगे, and that's why the difference that you are expecting to see will be actually a lot lower, and then you will actually get a wrong result, which is जो आपको अलग कम number of operations बताएगा. It should have been bigger. So therefore would have to focus on element wise operation, right? तो छोटे element हैं उनको increase होना है, so इसलिए उनको अलग से count कर रहे हैं. जो बड़े elements हैं उनको decrease होना है, इसलिए उनको अलग से count कर रहे हैं. And when we have find out this, then only we finally add up and divide by k to get the correct operations. It directly sum of the subarray minus this median value would not be the correct approach, क्योंकि उस केस में the smaller elements would be compensating the difference for the bigger elements, and therefore you will be getting a much smaller answer which would be inaccurate, right? So ये है इसका approach कि you find a technique to find the median efficiently. You find, you get this some of the smaller and lower elements, and you get this. Okay, now I'll just discuss कि आप how you can actually efficiently find this medians and everything else. Here you can actually, there are a lot of different data structures. First of all is basically persistent segment trees. Okay, persistent segment tree is a way to solve this problem. ठीक है, so persistent segment tree, you can say it's actually a way of storing the versions of a tree. Okay, versions of an array. Okay, so let's say कि एक array है जिसमें लगातार अपडेट होते जा रहे हैं, चीजें हो रही हैं. Okay, so what persistence, you understand? Persistence is basically, we are able to include the history. Okay, we are able to persist the information that we already have. So that is how persistent segment tree comes in. So basically क्या होता है, उसमें एक ही segment tree में उसके multiple versions create हो जाते हैं with different roots, right? We have different roots जो कि अलग अलग versions को देखते हैं. फॉर एनी सॉफ्टवेयर जो भी आप यूज भी करते हो, आप देखते होगे, वी हैव मोर और लेस एवरीथिंग इज सेम, जस्ट सम फंक्शनैलिटीज आर चेंज, राइट? लेट्स से ये कोई सॉफ्टवेयर था 1 2, ठीक है, अब इसमें कुछ नया टॉप ऐसे चेंज किया मैंने, एंड नाउ आई नो कि दो बेसिक अंडरलाइंग फीचर्स हैं, दे आर गोइंग टू बी सेम. सो व्हाट कैन आई डू? आई कैन कनेक्ट दिस टू दिस, and since they are already connected, so you can see this is version 1, this is version 2. This is somewhat a very vague picture of persistent segment tree looks like. Okay, this is one way. अब वो कैसे करोगे वो आपको देखना पड़ेगा. We have to find out. It is actually very complex. I'll not tell that. Okay, another way is basically using Moore's algorithm. Moore's algorithm is very widely known as the square root decomposition way, where you basically divide an array into blocks. Okay, into blocks. You divide a complete array into some blocks. Generally, the size of these blocks is taken as a root n, and where n is the size of the array, and then you calculate the queries efficiently. And this specifically for offline queries where you cannot update anything. Okay, more, and since we know हमारे question में we are not going to update any value in the array, right? We are just querying to get the count, right? We are not changing any value. That's why Moore's algorithm, and along with it, to find the the median, to find the median as well as the sum, as well as the sum of the values, you can actually use a bit. Bit is basically binary index trees, or you popularly known as that Fenwick trees. Okay, so it's basically a combination of both these. You can handle it either by using persistent trees, persistent segment tree, and binary search, or you can also go for Mohs algorithm plus BIT Fenwick tree, where basically Mohs algorithm is for processing the queries and finding the median and sum in fast time and log n time will be done by using a bit binary index tree Fenwick tree. The rest I will leave it up to you. You can go for other solutions. You can look up at different codes as well. Okay, so yep, let me just yeah. So this was how this question was meant to be. In the possible time complexity for the solution can be n plus q whole multiplied by root n, which is basically the time complexity for Mohs algorithm. You can also use merge sort trees. Merge sort trees also is an advanced data structure where you basically, instead of sorting a single element or a single feature, you basically store the complete values. Okay, you store the complete sub-arrays. Okay, that is a merge sort tree. Merge sort tree, the space is n log n, and the time complexity for query would be log n square. Okay, and for persistent segment tree, you'll get n log n, but it's a bit more tricky. Okay, and for Mohs algorithm, again, it's q root n, because you can see the constraint is 10 to the power of 4. That's why you can easily pass the time constraint, because n is 10 to the power of 4, square root would be what? Would be 10 to the power of 2, multiplied would be 10 to the power of 6. So you can easily pass the time constraint. So that is also a way. So this brings an end to our discussion of the contest 478. I hope you like the problems, the solution of the problems, the discussion, how to approach these problems, and what would have been the best strategy to solve the problems. The first three were very easy, while the fourth one was very was very mind blowing problem. It will take time. It will also, it might not be possible for a lot of people to come up with a solution within the next 1.5 hours. Okay, and to even if you're coming up with the logic, then implementation would take time. It is heavy, and that is all. Do drop a like, do comment, do subscribe, do share with your friends and peers. You can also comment your own approach that you followed for solving any problem. Let's say if you had a better approach, or a more short, concise way of solving a problem, or you would have a better, different, completely different logic for a problem. Do comment, do share. If you were able to solve how many problems, three or four, or only one, not an issue. And yeah, give constructive criticism as well. What you would like to see, what you want to see, and what else I can do. Until then, signing off. Bye bye. Keep grinding, keep practicing. Bye, guys.